So now we need to discuss solving problems with interacting objects. In this case, we have 4 people lined up. We have Joan, Elizabeth, Trinkle, and Bera. Joan pushes back on the ground with a force of 2,000 newtons, which means the ground is going to push forward on Joan with that same force. Every action has an equal and opposite reaction force. Before we look at anything else going on, we need to see what's going on behind the scenes. And again, as with all systems problems, you're going to be following 2 rules. Number 1, you will look at the objects as a full system. And then number 2, you will solve for the forces on individual objects. And I'm going to add a little star saying, work your way from the outside objects in. And I'll show you why I recommend that in a moment. If we look at this exploded view of each of these 4 people, and yes, I realize how ridiculous of a name Trinkle is. Don't blame me, blame the Austrians. But if we look at the individual forces on each of these 4 people, this 10 kilogram person, this 5 kilogram person, 3 kilogram, and 1 kilogram person, all lined up as you push 1, Joan is going to push Elizabeth, and Elizabeth is going to push Trinkle, and Trinkle is going to push Bera. But every action has equal and opposite reaction force. So now, Joan pushes ground, which is not a part of the system, but ground pushes Joan. Joan pushes Elizabeth, but reaction is Elizabeth is going to push Joan backwards. And as Elizabeth pushes Trinkle, Trinkle is going to push Elizabeth backwards. As Trinkle pushes Bera, Bera pushes Trinkle backwards. And of course, there is a coefficient of friction. So we need to consider that when we're looking at each of the 4 objects. So we need to make sure we add it in as the forces. So now let's look at the exploded view for each of these 4 people. If we look at the forces on Joan, we have the force of the floor on Joan. And which way is the ground pushing Joan? It's pushing her forward. So the force of the floor on Joan is forward. We have the force of Elizabeth pushing Joan backwards. And of course, because Joan's net motion is forward, that means friction is going to oppose that intended motion. Friction is always working against your intended motion, or in this case, your actual motion. So we have the force of the floor forward and Elizabeth and friction backwards. If we look at the forces on Elizabeth, we have Joan pushing her forward, we have Trinkle pushing her backward, and her intended motion is forward. So you also have the force of friction on Elizabeth backwards. When we look at Trinkle, we have Elizabeth pushing Trinkle forward, we have Bera pushing Trinkle backwards, and we have Trinkle's unique force of friction based on her weight. And Bera, she's only being pushed by 2 objects. We have Trinkle pushing Bera forward and her own force of friction. There is nothing else pushing her backwards because she's not pushing into another object. And that's why I recommend this rule number 2. Solve for the forces on outside objects first and work your way in, because there tend to be less unknowns on the outside forces. If we look at this specifically, we don't know the force of Trinkle on Bera, but we can calculate the force of friction on Bera, which means if we already know the acceleration, there's only one unknown. The same is true for the force on Joan. We know the force of the floor on Joan because it's equal to the force of Joan on the floor. And we can figure out Joan's force of friction based on her normal force, mu Fx. Force of friction is coefficient of friction times the normal force. And her normal force is equal to her weight. Which means the only unknown after we solve for acceleration, of course, would be the force of Elizabeth pushing back on Joan. So you should always work your way outside in. If we look at Elizabeth, we don't yet know the force of Joan on Elizabeth, and we don't yet know the force of Trinkle on Elizabeth. The same is true for if we look at the force on Trinkle. There will be 2 unknowns after we solve for acceleration. So right now, these have 3 unknowns, and these only have 2. But once we solve for acceleration, these will only have one unknown in their net force equation, which is solvable. But we still don't have acceleration. And that's why we need to look at the objects as a full system. So if we start over here, and I'm going to move my coefficient of friction a little bit higher up. Mu equals 0.1, and that's between all of their shoes and the floor. So we have Joan, Elizabeth, Trinkle, Bera on the floor. Now, the only outside forces, we have the force of friction of this person plus this person plus this person plus this person, but since they all have the same coefficient, we have a total force of friction of Joan, Elizabeth, Trinkle, Bera. That's just one force of friction equal to the coefficient of friction times the normal force for all four objects added together. 10 plus 5 plus 3 plus 1 is going to give us 18 kilograms, which means we can find the normal force because the vertical forces in this case are balanced. So gravity, normal force. Before I start calculating anything, I should look at any other outside forces. Oh, we also have the force of the floor pushing in on Joan. So we have the force of the floor on Joan also acting on this. The reason you don't include these other forces is every action has an equal and opposite reaction force. And I'm going to destroy this exploded view, subtracting forces that are inside. So the force of Trinkle on Elizabeth, the force of Joan on Elizabeth is equal to the force of Elizabeth on Joan. And this is when we're looking at the entire group as a system. We're going to add these forces back in when we look at the individual forces. We have the force of Trinkle on Elizabeth balanced out by the force of Elizabeth on Trinkle. We have the force of Bera on Trinkle countered by the force of Trinkle on Bera. And then what we're left with, Trinkle on Elizabeth. Did I cancel that one out? I did, with Elizabeth on Trinkle. So those cancel, and those cancel. So the only forces we're left with is friction plus friction plus friction plus friction, which is the total force of friction of all four objects added together, plus this unbalanced force of the floor on Joan. So those are the only forces that remain, force of floor on Joan and the force of friction for the four combined objects. And now we can start looking at calculating the forces of the system. Force of gravity is mass times gravity. 18 times 10 is going to give you 180 newtons. And our vertical forces are balanced, so that means the normal force has to be 180 newtons. The force of friction of this entire Joan, Elizabeth, Trinkle, Bera system is going to be the coefficient, 0.1, times the normal force, 180. And when we multiply that out, you're going to get 18 newtons of force. That's the force of friction for the system, or Joan, Elizabeth, Trinkle, Bera. And we do know the force of the floor on Joan, because Joan pushes back on floor with 2,000 newtons, but in Soviet Russia, floor pushes forward on Joan with 2,000 newtons. So now, if I can get a calculator, we can start to do our work on this object. This is one of those moments where I recommend you consider pausing the video so that you can attempt to calculate the acceleration of the system on your own. So now we're going to create a net force equation for the system, and that's equal to the mass of the system times the acceleration. Well, the net force would be rightward forces minus leftward forces, because forces to the right are positive, forces to the left are negative. So we have 2,000, I should write this in terms of variables. So we have the force of floor on Joan minus the force of friction of Joan, Elizabeth, Trinkle, Bera, and that's equal to the mass of the system times acceleration. Force of the floor on Joan is 2,000 newtons. Force of friction is 18 newtons. The mass is 18 kilograms times the acceleration. At this point, it's simple algebra. 2,000 minus 18, and then all of that divided by 18 should give you a really small acceleration of 110 meters per second squared. Okay, it's a little bigger than I anticipated. Ouch. So now that we know the acceleration of the system, they're all going to accelerate together, which means we know the acceleration of Joan, we know the acceleration of Elizabeth, Trinkle, and Bera. And we need to plug that acceleration in for each of the objects, and that way we can find all unknown forces. We can find the force of Joan on Elizabeth, we can find the force of Elizabeth on Trinkle, we can find the forces of Trinkle on Bera. And those are the only forces we need because Bera on Trinkle is the same as Trinkle on Bera, Trinkle on Elizabeth, the same as Elizabeth on Trinkle, Elizabeth on Joan is the same as Joan on Elizabeth. Basically, you need to find how hard each person pushes the next, and that's plenty. You solve for every force in the situation. But remember, we decided we were going to discuss outside forces first. I'm going to go ahead and solve for the forces on Bera. So if we have Bera here, who's a 1 kilogram girl, and she's pushed forward by the force of Trinkle on Bera, how hard Trinkle pushed her forward, but she has her own force of friction she needs to overcome. Force of friction on Bera, we have force of gravity down and normal force up, but those should cancel each other out. So the force of gravity should be 10 newtons, 1 times 10, which means the normal force should also be 10 newtons. We can plug that in to figure out what the force of friction is. Remember, FF is mu Fn. Her normal force was 10, and her coefficient of friction is 0.1. So 0.1 times 10 is going to give the force of friction of 1 Newton. We still don't know FTB. And that's what we're ultimately trying to find. We're trying to find the forces each one applies to each other. So now we can plug it into a net force equation for Bera. So let's come up with a net force for Bera equation. It's the mass of Bera times Bera's acceleration. The net force would be FTB minus the force of friction equals her mass times her acceleration. And at this point, we can plug in numbers. We don't know FTB, but we know the force of friction is 1 Newton, and that's equal to 1 kilogram times 110 meters per second squared. And with some algebra, you should get 111 newtons equals the force of Trinkle on Bera. And now we need the force of Elizabeth on Trinkle, which should be the same as the force of Trinkle on Elizabeth. And keep in mind, we're working our way outside in. I've already done this, which means I can probably solve for this one too. So let's look at the forces on Trinkle. Just like we already drew up here, we have the force of Elizabeth on Trinkle pushing her forward, the force of Bera on Trinkle backwards, which is the same as the force of Trinkle on Bera, and her own force of friction, the force of friction of Trinkle. Normal up, gravity down, but they don't matter in our net force equation because vertical forces don't affect the horizontal forces, and they are independent when we're calculating the acceleration, or at least in our net force equation. We know the force of gravity for this 2 kilogram object should be 20, which means the normal force is 20, which means the force of friction is 2 newtons. If you're not sure how I got 2 newtons for the force of friction, see how we calculated the force of friction any of the previous 3 times. And then we can create a net force equation for Trinkle. That's equal to mass of Trinkle times the acceleration. And without plugging in every single force, I'm going to skip a step because hopefully at this point we're okay. And you can review and see if you can make the leaps that I'm going to start to make as we continue with the same process. We don't know the force of Elizabeth on Trinkle minus the force of Bera on Trinkle. Bera on Trinkle. I switched my capital versus lowercase, but we know that should be 111 newtons minus the force of friction, which is 2, and that's equal to 2 times the acceleration, which we already know is 110. So 220 plus 2 plus 111 equals the force of Elizabeth on Trinkle. And that should give us 333 newtons. And now the only remaining force is the force of Joan on Elizabeth. So you could use either of these objects at this point and get the same answer, because we have to work our way outside in. And if we have this, and we have this, this is fair game, and this is fair game because they're both on the ends. So let's look at the forces on Joan. You could do this the other way. You could have calculated the forces on Elizabeth, and you should get the same answer. So the forces on Joan, we have the force of the floor on Joan, normal, gravity, force of friction for Joan, and the force of Elizabeth on Joan. And this was force of floor on Joan. I don't know if I've missaid that before. But we're going to do a net force system, or net force equation for Joan. And that's equal to the force of the floor on Joan, which is 2,000, minus the force of Elizabeth on Joan, which we don't know, minus the force of Joan's friction, which should be 10 newtons, and that's equal to her mass times her acceleration. 1110 minus 10 negative FEJ 2,000. Ooh, this is going to be a big force. Maybe not. So the force of Elizabeth on Joan should be equal to 880 newtons. And assuming I haven't made a math mistake, which is entirely possible in this long of a video, this should be sound, and you should get the same answer if you looked at the forces on Elizabeth. But I've run out of board, and I've run out of explanation, and that's what I have for now.